Welcome to review lecture 9.2, the magnetism of matter. Upon successful completion of this unit, you will be able to describe the magnetic behavior of materials and describe the three types of magnetic material. Okay, there are three types of magnetic material. Diamagnetic, which is as common as water, literally. Almost everything is diamagnetic, including you and me, mostly. It's repelled from regions of strong magnetic field. So it sort of behaves the opposite of what we think of magnetic attraction. It gets repelled from magnetic field. It is the weakest of all interactions, and that's a good thing. Paramagnetic is fairly common. It's attracted to regions of strong magnetic fields, and examples are liquid oxygen, aluminum, calcium, platinum, and glass. Ferromagnetic materials is the kind of thing we think of as being magnetic. This is exhibited by only a few elements and compounds such as iron, cobalt, nickel, neodymium, rare earth. This is attracted to regions of strong magnetic fields. The atoms in these materials have permanent magnetic dipoles that are caused by electron spin and orbital motions, which can easily align with an external magnetic field. And therefore, they have a magnetic memory wherein they can retain their magnetism even when they're not in an external magnetic field. These are the so-called permanent magnets, or what we call refrigerator magnets. Magnetic fields in atoms are produced by two types of electron motion. Electron spin, and we model an electron as basically a spinning ball of charge. Now, this is kind of what models something in quantum mechanics with something that's every day. So it's not exactly a good model, but it's good enough for this. This is the main contributor to magnetism. Pairs of electrons spinning in the same direction will create a stronger magnet, and electrons like to go in pairs. Pairs of electrons spinning in opposite direction cancel the magnetic fields out of each other. The other type of electron motion that produces magnetic fields is the electron revolution around the nucleus. In this model, it acts like a tiny current loop with its own magnetic dipole. Now, neutrons and protons also produce magnetic fields, but these are more than 1,000 times weaker than those produced by electrons, so we generally can ignore them. So we don't consider them important now, but all magnetic fields are produced by the relative motion of moving charges. Relative is the operative word there. Okay, now what are magnetic domains? Magnetic domains are magnetized clusters of magnetically aligned atoms. And basically, this occurs in ferromagnetic material. Permanent magnets are made by aligning the domains by placing pieces of iron or similar magnetic materials, such as ferrous materials, in a strong magnetic field, or by stroking the ferrous material with a magnet to align the domains, or running a strong current through the ferrous magnetic material, or anything you can do to disturb this. Okay, if you have this in a strong magnetic material, in a strong magnetic field, you can even hit it with a hammer, and that will have a tendency to jostle these things. They'll rotate until they line up with the magnetic field. So what happens? Now, for most elements that are lying around, the magnetic moments of the atoms are randomly arranged when the atoms join together to form a solid. Now, this random arrangement produces a solid whose net magnetic moment is very close to zero. So the atomic magnetic moments, due to the unpaired electrons, point in random directions. The sample has no net magnetic moment. Now, what happens if you put it in a strong magnetic field? A few substances, such as iron, cobalt, nickel, neodymium, in these substances, these are called ferromagnetic substances. The atomic magnetic moments tend to all line up in the same direction. Materials that behave in this fashion are called ferromagnetic. Ferro meaning iron-like, because iron is the first one that people really discovered. So a typical piece of iron is divided into small regions. These are typically less than 100 microns in size. These are called magnetic domains. Magnetic moments of all the iron atoms within each domain are perfectly aligned, so each individual domain is a strong magnet. So your paper clip is like this, or your knife, okay, a chunk of iron looks like this. And inside this domain, for instance, they're all lined up in this direction. Okay, but in that domain, they're all lined up in that direction. In this domain, they're all lined up in this direction. Now, these all cancel out because they're randomly arranged, so the overall magnetic field cancels to zero unless you do something like this. If a ferromagnetic substance is subjected to an external magnetic field, the external field will exert a torque on the magnetic dipole of each domain. This torque will eventually cause many of the domains to rotate and become aligned with the external field. This adds to the overall magnetic field. And this effect is used in making electromagnets, transformers. It's used in making magnets. So here we have a ferromagnetic material right here, and we subject it to a strong magnetic field, say from an electromagnet, a coil with a current running through it. And typically we put this inside the coil where the field is strongest. And what happens is all these individual domains that were randomly aligned turn so that they achieve a minimum energy state and they line up. So if we place a piece of iron, a ferromagnetic material, inside the coil of an electromagnet, we can use this to enhance the magnetic field in the coil. Magnetic domains in the iron are induced into alignment by the magnetic field in the coil, increasing the magnetic field intensity. But beyond a certain limit, the magnetic field in iron saturates, because after a while, these all get lined up, and there's no more to join the club, so to speak. So that's called saturation. So iron is not really used in the cores of the strongest electromagnets. Instead, we make the coils out of superconducting materials and we cool them so that they can carry extremely large currents with very little electrical resistance and heating. Now, this is a simple electromagnet. Anybody can make something like this. All you need is some thin wire, thin coated wire, and something metal. Iron is the best. And I did this at home when I was a child. I took a nail, a large nail, and somebody's making a deck in the neighborhood, and I got a hold of a nail. And I had some transformer wire. And I wrapped the nail in the transformer wire, and I looked around for a battery, couldn't find one, and stuck it into the wall outlet. Please don't do that at home. My mom was really mad at me. All the lights went out in the kitchen upstairs, and I could hear my mom yelling, "Carol, what are you doing down in the basement? All the lights are out upstairs. What did you do down there? We won't be able to sell the house." Poor woman. She grew up with 4 kids like me. Okay, so how does a magnet induce magnetic behavior? Well, nearby strong magnetic fields will induce the magnetic dipoles in nearby ferromagnetic material. An induced magnetic dipole always has an opposite pole facing the original field. So in this case, that would be the solenoid. Remember that opposites attract. So the magnetic force between these poles pulls the ferromagnetic object to the electromagnet. Now we can explain how a magnet attracts and picks up other ferromagnetic objects, even if they are not really permanent magnets. So the electrons are microscopic magnets. Through their spin, a ferromagnetic material in which the spins are aligned is organized into magnetic domains. The individual domains align with an external magnetic field to produce an induced magnetic dipole for the entire object. This effect can be passed on to other nearby magnetic materials. So in other words, you can pick up a whole daisy chain of paper clips. Okay, so for instance, you have a magnet, a strong magnet, and you pick up one paper clip. What this does is this induces this paper clip to become a magnet on its own. So there's a south pole here and a north pole there. If you get this north pole near another paper clip, it may attract it, so it'll create a south pole here and another north pole there. So you can keep on doing this. Now, this only works with ferromagnetic materials. It won't work with things like copper. Copper is not ferromagnetic material. So an object's magnetic dipole may not return to zero when the external field is removed because some domains rotate and lock and become frozen in the alignment they had in the external field. So thus a ferromagnetic object that has been left in an external field may be left with a net magnetic moment even after the field is removed. In other words, the object has become a permanent magnet. I use the word permanent loosely. In unmagnetized iron, the domains are not aligned with each other. If you place the unmagnetized iron in a strong external magnetic field, then the atoms and the domains will begin to align with the external field. As the atoms are aligned, their effects add, the magnet gets stronger. Eventually, all the domains are aligned and the magnet cannot be made stronger. That's saturation. If it turns out that it's left there long enough and it develops a permanent magnetic moment, so in other words, all the domains align, you wind up with a permanent magnet. Now, if you break a magnet in half, it results in 2 equally strong magnets, each with a north and a south pole. There's a difference between a permanent magnet and a temporary magnet. Permanent magnets have an alignment to the domain that remains once the external magnetic field is removed. A temporary magnet is like picking up a paper clip with another magnet. So then the paper clip wasn't originally magnetized. In that type of situation, the alignments and domains returns to a random arrangement once the external magnetic field is removed. Any piece of iron in a strong magnetic field will be magnetically induced to become a temporary magnet until the magnetic field is removed. Ferromagnetic materials are attracted towards strong magnetic fields. If you leave it in a strong magnetic field long enough, eventually you can become a permanent magnet. Permanent magnet is a loose term. Any permanent magnet can be demagnetized by heating it past the Curie temperature. Why? Well, remember, it requires alignments of the domains. What happens when you heat something? The atoms start moving around quickly and jiggling themselves out of that alignment. Okay, so in other words, they won't retain the magnetism because they'll be thermally agitated and they'll lose their alignment. You can bang it or drop it. That does the same thing by vibrations. You can do anything that will disrupt the alignment of the domains will demagnetize a permanent magnet, an otherwise permanent magnet. Thank you.